Okay, I'm going to open up today with a vending machine. A vending machine is a function. Okay, if I were to call this machine F, I could say that F of, and say I can't really read these numbers here, but say I put in D6. Okay, and I could say F of D6 gives me M&Ms. Okay, or F of, say, F8 gives me those Milano cookies. Those look pretty good. Okay, so the Milano cookies down there at the bottom. Now, the reason that a vending machine is a function is the rule of a function is that an input cannot have multiple outputs. Okay, and that would be terrible for a vending machine. If I were to input F8, I want to know I'm getting Milano cookies. I don't want to wonder if I'm going to get Milano cookies or I'm going to end up with that apple, right? I don't want that. I want to know that if I put in a certain input, there's only one possible output, all right? And that's the requirement to be a function. Now, the function that we have in this vending machine is not what is known as one-to-one. Okay, because I could put in, say, D6 and I could get M&Ms. I could also put in, say, C7, right? And also get M&Ms as an output. There's 2 rows of peanut M&Ms. There's 2 rows of plain old chocolate M&Ms. Same thing for those Milano cookies, right? Say this were F8. I could also put in something else like, I don't know, G2 and also get out the Milano cookies. All right, so if different inputs give me the same output, all right, I can get Milano cookies by 2 different inputs, then my function is not, so it does pass the definition of a function, but it is not 1, 2, 1, meaning I can get the same output with different inputs. Okay, for a vending machine to be one-to-one, there would have to be a different item in every single row. Okay, I couldn't have any repeat outputs. Okay, but because I have repeat outputs where different inputs give me the same output, then my vending machine function is not a one-to-one function. All right, so that's going to come into play in a little bit. Okay, we're going to start talking about in this segment inverses. All right, and for the most part in math, if you can do it, you can undo it. All right, and I say for the most part because there are things that I can do that I can't undo. For example, I can multiply by 0, but I can't divide by 0. Okay, so I can't undo it. Okay, but if I added 3 to a number, I could undo that by subtracting 3. Okay, so the inverse of adding 3 is subtracting 3. That's how we undo it. And the inverse of dividing by 3, so how do I undo dividing by 3? Right, I multiply by 3. All right, and you used inverse operations in learning to solve equations. Right, so these are things you've worked with before. And what your high school teacher taught you about finding inverses is you were probably taught, and we know f of x or g of x is y, right? So you were probably taught to do this. Switch the x and the y, all right, to get this inverse function. Here's the work. I mean, I knew what the inverse function was by common sense, but you were taught to do this work. You were taught to switch the x and the y and then solve for y. So you would get the x minus 3, but then this would be the inverse function. All right, and same idea here. X equals y over 3. You would multiply both sides by 3 And then this y you would have to recognize is the inverse function of what you started with. Here's something else that happens when I work with inverse functions. All right, so something else that I should know is that if I wanted to find, say, f of 7, okay, if I put that into this original function, I would get 10, right? F of 7 is 10. Now, if I put my answer into the inverse function, right, I would get back to 7. Okay, so inverse I can see switches the x and the y, right? The y here became the x here, right? The x here became the y here. And another thing that we're going to look at when we start doing compositions of functions, which, oh, wait a minute, we did those the other day. I'm thinking we haven't done that yet. When I do this, right, compositions of functions, this means that, wait, I want a 7 here. Just write it in red. 7, right? F of 7 was 10. And then when I find F inverse of 10, I get back to 7. Okay, so the composition, right, of F inverse of F of 7 gets me back to 7. So what about finding inverses? So this is how I do it algebraically. What about finding inverses graphically? All right, so we know that to find inverses, you switch x and y. So let's look at this point here, which would be the point 1, 6. Okay, the inverse function would have to take the point 1, 6 and switch x and y. So the point 1, 6 becomes the point 6, 1, right? When I take the inverse, if this is a point, 1, 6 is a point on the graph, right? Or this represents a pair of values where f of 1 is 6, then for f inverse, sorry, that should be a parenthesis. For f inverse, then f of 6 would have to be 1, okay? What were you doing? Think back to transformational geometry. What were you doing when the x's and y's switched? What kind of transformation? Right? Think about the transformations you did. Like you reflected through x, it negated the y, reflect through y negates the x, right? Rotations of 90 degrees, switch the x and y, negates either the x or y depending on which way you go, right? Reflections through the origin, negate the x and the y, right? Remember all this from geometry. What were you doing when the x and the y switched? Okay, so again, let's look at another point. Let's look at the point 2, 3. Oh, wait, that's 2, 2. 2, 3 would be right here. 2, 3, the inverse would be 3, 2. So what would make these points map to one another? Okay, and I hope you recall, I'm going to attempt to draw a straight line, which is not very easy to do with my cursor. That's not bad. What you're doing is reflecting through the line y equals x. Okay, so see how that's equal distance, right? If I connect these points, you've gone equal distance, right? This would be a right angle. So this is a point reflection through the line y equals x. Okay, so graphically, that's what I am doing. That's what transformation I am doing geometrically when I switch x and y. So let's go to the handout and do just a little bit on the handout before I will give you another break. So let's go here. And it says graphically, I can find the inverse of a function by, so that's what we just noticed. by reflecting through the line y equals x. Algebraically, all right, so this is what we just talked about on the other page. Algebraically, I can find the inverse by interchanging x and y, then solve for y. All right, so what I've actually shown you here in red, so the blue line is the line y equals x. We are getting close to a midterm where I'm going to ask you to identify common functions without a calculator. All right, this function in red, I wouldn't say it's one of our most common functions, but this is something I would want you to be able to identify. Okay, this function is actually the cubed root of x. All right, or in other words, the cubed root of x is x to the 1/3. All right, what's the opposite of the cubed root? Right, and all of you would recognize if I were to find the inverse algebraically, all right, if I switch x and y, and then I solve for y, right, I would cube both sides. You get y alone. Okay, so the inverse of that would be y equals, sorry, it's really hard to write a good 3 here. Y equals x cubed. Okay, but again, in order to do this algebraic or do it graphically, I want you to reflect the red line through the blue line. All right, so reflecting through a line means I go equal distance. Okay, so I go any point like this point to its image, I have to go perpendicular to the line, equal distance, right, like this. So this should be a right angle, and these distances should be the same. Okay, so you take a minute to complete that drawing, and I hope you're able to recognize that you are in fact getting the equation y equals x cubed. So that would be the inverse. All right, so sketch that in, and then come down below and sketch this function. So this is the function y equals x squared. All right, reflect that function in red through that blue line and take a look at what you get. All right, so let's stop here and take a break, reflect that line or reflect that function, and then we'll pick back up.